Again, I'm Jenna. This is Parsing Parsers, and I am a senior front-end engineer at Slack. I'm on the search and discovery team. We're based in New York City. I spend a lot of time thinking about the quick switcher and other autocompletes throughout the product. Some other things I do in New York include organizing 2 JavaScript communities. One is Empire.js, which is an annual JavaScript conference. The other is Brooklyn.js, which is a monthly JavaScript meetup. So I know firsthand how much effort it takes to pull off an event like this. So can we get a round of applause for all of the organizers, volunteers, and everyone else? So my Twitter handle is Zeigen Vector. You can feel free to tweet questions, comments, and compliments at me there. I will also tweet out the link to my slides, which just happens to be on this slide. I should also mention there's a lot of information here. So I've included some citations at the bottom of my slides. There's probably like entire college courses on parsers, but I had to do this in 25 minutes. So there's going to be a lot of information in a short amount of time. Some of it's going to be high level. Some of it's going to be fast. Sorry. So if you want to learn more, please check out those links. All right, let's parse some parsers. So I think to really understand parsers, like understand what they're doing, we need to learn a little bit about what makes languages languages. So we'll talk a little bit about that. And then as I was building the talk, I just realized that the best way to learn about parsers is to build one, which we will be stepping through the code for, because I'm not brave enough to live code on stage. So it'll be small, it'll be a little toy parser, and hopefully you can learn some things that I learned and feel the joy that I felt while building it. So let's learn about language. Language is a structured system of communication. Might seem obvious, but we're starting at the basics here. So we are using language to encode information to send between 2 entities, like 2 people, 2 computers, a person and a computer, etc. The language that we're used to is called natural language. We humans, we speak it, we sign it, we write it. We understand it innately because our brains evolved to understand it. There are rules that govern how we put words together and how we put letters together to form words, but we don't necessarily know these rules explicitly. We might learn them in English class or in whatever class like that where we learn the rules of grammar, but we don't necessarily know these rules explicitly. Some of these rules might be that nouns combine with verbs, an adverb might come in to modify that verb, but again, we understand language and we learn these rules without ever even really trying, because our brains have evolved seamlessly to acquire language. And even if we break these rules, it's okay. You generally understand what the other person is trying to say. Formal languages, on the other hand, are a bit more, well, formal. They're more math class than English or Spanish class. Formal languages are also made up of words that are made up of letters from an alphabet, both of which can be combined at each level based on specific rules, which is called the language's grammar. Programming languages are formal languages, which mean, too, that they have an alphabet like Unicode and a grammar, which we sometimes call the syntax, that tells us how to write our code, all the way down to the punctuation. So as I said, a language's grammar is the set of rules for that language. Formal grammars put these rules in terms of rules of replacement, which are called production rules. So to get a sense of what I mean by replacement, let's take a look at this little sentence diagram for this very short sentence Jenna gave the talk. So we can kind of see that a sentence can be broken down into a noun and a verb phrase. A verb phrase can be replaced by a verb and a noun phrase, etc., all the way down the line. So here are these rules put another way. So you can see that sentence, noun plus verb phrase, verb plus noun phrase. Noun phrase can be broken down into a direct object and a noun, and neither of these can be broken down any further. Programming languages have their grammars defined in a spec. If any of you have ever been brave enough to try and read the ECMAScript spec, you might have seen that there's a section on grammars, and a good chunk of it is describing how we put the bits of JavaScript together to create proper JavaScript. So let's start our journey towards building our parser and first define our language and its grammar. So I wanted to choose a language that had a few moving parts that I knew well and that I could explain how it works and what it means. So I chose a language that was right there in front of me every day, 7 days a week. You might be familiar with it. It is the search query language from Slack. If you're not familiar with it, explain what's going on here. And our goal ultimately will be to build an even better visualizer for this language. So here's an example of the search query language we have. There are terms here, like JavaScript, phrases like front end in a single round of quotation marks. There's these filters, like in random and in general, which say which messages we want to find, which channels we want to search for messages in, and from filters, like from Jenna, you want to find all of the messages that are from me. So here's what this grammar is going to look like. A query can just be a term. You can search for just JavaScript. A query can also be a term plus more query. If we were to lop JavaScript off the beginning, that would still be a valid query. Query can just be a filter. You want to search for all of the messages in random, you can just do that. And then you can search for all of the messages that have the word JavaScript in them in the random channel. And that's our little grammar for our language. Then I want us to build something that looks like this, that highlights the different types of bits of language in their own color, whether it be green, purple, or light pink. Okay, parsers. That's what we are all here for. So what is a parser? Well, it parses, which is the process of analyzing language against the rules of its grammar. So we're going to take the language and break it down into its components to find its underlying structure, to see if it adheres to the rules of the language that it was written for. This process also helps us turn the language into something the computer can better use and maybe understand if we're going to think about it in human terms. Parsers can be really complicated, but in the end, all they have to do is be a function that takes raw input and turns it into meaningful data that is created from the input, or it's going to send off an error. So if it takes some unstructured language and turns it into something that is more structured and is more meaningful, that's a parser. Parsers, in general, when they're more complicated, they usually have two parts to them. They have a Lexer and a parser, which is the main event, because it takes on the whole word, right? So the Lexer is going to take the text and break it down into meaningful units called tokens. These meaningful units are going to be the words, the punctuation, etc. The first step in lexing is going to be the scanner. So it's going to go through and break the string of characters into the proper chunks, which are called lexemes. And these lexemes are the words in the language. They can be keywords, literals, like a number or a string, punctuation, etc. And this process is often accomplished by using regular expressions. So let's dig into some code. Okay. So we're going to look at the other one. This one. All right, so we have our regular expressions here that define the 4 types of things that we can have: an in filter, a from filter, a phrase within those quotation marks, and just a single term, so just one word. And this is pretty much just going to be our Lexer. It's going to take those regular expressions and match them against the string that we put in. So let's see what happens when we use our example a little bit. So we can see here that these are our lexemes, just some smaller strings made from the initial input, which was JavaScript, front end, in general, from Jenna, etc. Cool. So let's also take a look at what JavaScript is doing, because that's also interesting. So JavaScript is going to take this little snippet of code and turn it into something that looks like this. Not very different, but you can see it's going to break it down into its lexemes, which include just const, the variable name lexeme, that equal sign, which is punctuation. The next step is the evaluator is going to combine the lexeme's type with its value to create a token. So first, let's take a look at our code. And you can see this next little bit is our evaluator. So we're going to take the tokens and combine them with their type, which we can figure out because we know exactly what an in token looks like based on its regular expression, what a from token looks like based on that, and et cetera. So we can take those and turn them into the types of tokens that they are, which is just like a little object wrapper, nothing too complicated, because again, little language, little parser. So JavaScript is going to take its lexemes like this, and it's going to put them up into the, mash them up with their type, and turn them into these tokens. And shout out to Esprima here, which is a very popular parser that folks use for JavaScript that backs some of our favorite JavaScript tools that do like source transformation. Demo tool's linked at the bottom, so if you want to see how it shakes out with whatever your favorite snippet of JavaScript is, you can do that there. And this is what it is actually going to spit out. It's really simple. It has this type and just a value. Never showed you what our little parser ends up doing, so let's look at that. If I can. So, actually, no, they're right here. Hello, tokens. These are the tokens from our little language. So we have term and infilter. See, not too much more complicated, but they still have a little bit more meaning. We know that this is an infilter, this is a from filter, and that's something that the computer might be able to do a little bit more with than just those bare strings that we had from the lexemes. All right, so now we're on to the main event, the parser, which is going to analyze the tokens that were produced by the Lexer, checking that the syntax is correct based on the prescribed rules of the language, while creating, again, that structure based on the production rules. The result of parsing is usually a tree. You might have heard about parse trees or syntax trees. So that's what usually gets created. And then if the parser cannot create a tree, you end up with a syntax error. So what we're going to want out of this is a tree that kind of looks like this, because that's what we need to build our visualizer. Parsers, in the end, are just around to help us achieve our end. We can build a parser in different ways to achieve different goals. And in the end, this is all we need. We need to know that all of these tokens wrap up into a single query. So let's take a look at our code and how it ends up spitting out our little tree. So I'm going to actually go to the VS Code. OK, so our parser isn't actually that much more complicated. So we're going to make a base query, which is going to be our top level, and just give it the tokens, because that's all that we need to create our parser the way that we need it to be created, creating this tree structure for our visualizer. So then let's take a look at what it spits out. Hello, parse tree. We have tokens. Well, the top level is the query, and then the tokens are here, spit out. We just have the single level. These don't get broken down any further. We are at the end. Cool. So JavaScript does something a little bit more complicated here. Going to have this program that eventually filters down into this tree. We have the, I can't help but notice that the leaves here are the thing that really matters, right? We have the variable names at the bottom, the strings, the method names. That's like the stuff that really has meaning to us. And then the rest of it was just there to help the parser figure out what was going on. And this is what a Supreme is going to spit out. It's a lot for such a little snippet of JavaScript, and this, I had to cut it off so you could even have a fighting chance of reading any of it. So it's a lot, but anything that helps us, helps the computer make our JavaScript do what we want it to do. I'm going to throw a little curveball into our little language here. I think that we should highlight these tokens, these entities, because they're their own separate meaningful unit, right? So what do we have to do to make our visualizer be able to do this? Well, first, we have to change our grammar around a little bit. Before, we had it so that a filter couldn't be broken down any further, but now it can into a modifier and an entity, which they themselves could not be broken down anymore. And then our tree is going to end up looking like this. It's a little bit more complicated, one more layer. Surely we can do this in our little parser with what we have. So let's take a look back at our code. Second round. Maybe, the first step is the Lexer, right? We're going to try and use our regular expressions. But I don't see a way for us to be able to use just these regular expressions and be able to maintain some connection between the in and the channel that we're looking in, or the from and the person. There's no way to maintain the connection between the modifier and their entity. But what we do know is how to decompose a in token into its modifier and its entity. We know that production rule. So if we can just, say, okay, this is our parser, we do what we want to. We know how to take an in token, and when we're tokenizing, we know how to take its lexeme and split it apart. We know that an in token, the modifier is going to be an in modifier, and we know that the filter is going to be this particular entity, which is anything after the in filter's colon and maybe a space. So we know how to break these two things apart because we know the production rule for turning an in token into its modifier and its entity. So why not? This is our parser. So then we can then make a mini tree out of this in token, and then we can, in our parse step, we still have these tokens that all roll up into that query. And we end up getting a tree that is a little bit more complicated. Bless you. So our tree is going to be one more layer deep. In token now turns into a modifier and an entity. Cool, cool, cool. All right, so now we're going to get into a little bit more theory, which is what this was all building up to. Why was the regex enough for the first example, but not for the second? This is, there's a lot going on here. It seems pretty powerful, right? We were able to pretty much encapsulate everything that we needed to do our parse for our first smaller language. But once we added that extra layer, the regular expression wasn't enough anymore to be able to really encapsulate the entire language's grammar. That's because the first language that we had was a regular grammar. That grammar was able to be described by this most simple type of language, which is called a regular language, that has a regular grammar. And all the production rules are of the following type. You have the thing on the left can be broken down farther. It is called a non-terminal. It's going to be a lot easier for me to use that term. And then the thing on the right cannot be broken down any further, and it is called a terminal. The other way that a rule can look is that a terminal can be broken down into one non-terminal and one terminal. So if we take a look at our little language, we end up getting something that looks like that. Either have the non-terminal on the left turning into something that can't be broken down any further, or it turns into a combination of just one thing that can be broken down further and one thing that cannot be broken down any further. But once we added in that next production rule, so we could break down the filter into a modifier and entity, ended up not being able to describe this with the regular grammar anymore. So the regular expression was no longer able to be just our friend, and we needed to add in something else that knew how to get that bit into our language and allow us to represent that as the structure that we needed. So the next level of complexity in languages is called a context-free grammar. It has rules that follow these rules. So the alpha, it's a little bit intimidating, but all it means is that it's any combination of things that can be broken down further and things that cannot be broken down further. And it's just a little bit more power that lets us do a lot more things. So the classic example here is that now we can do nesting, which includes matching parentheses. So regular expressions can't do this because they don't have any concept of memory. Whereas we need to know to verify if we indeed do have matching parentheses, if when we see a closing parentheses, if we'd seen the opening one earlier and not seen, or maybe we'd seen another opening one beforehand, but we need to have some type of memory to know if we are actually closing something based on the rules of the grammar. That's why you might have heard that HTML isn't parsable by regular expressions. Might be really tempting. Such a simple language. Of course it should be parsable by regular expressions. That's again because of the nesting. We need to know if our divs are closing properly. So, I mean, you might be thinking, oh, but look ahead in regular expressions. It's because regular expressions these days are more powerful than just a regular grammar. So they have that little bit of memory that's necessary to give it that little extra boost and make them just a little bit more powerful than just a normal regular grammar. So HTML, like most, if not all programming language grammars, fall into the context-free family. So you can do a lot with just this little extra bit of power, this little stack of memory that these parsers have. So I've been talking a lot about oh, this is like a toy parser. This isn't necessarily how these things necessarily work in the real world. It's because writing one by hand would be a little bit time-consuming. Most of the time, if you're going to build a parser for a language, you have a program that builds the parser for you, which is called a parser generator. So let's just go into what these things are doing at a higher level. So if we were doing this and following the more suitable way of doing it, we would end up lexing those terms down into their leaves. So we would end up with these terms, and then the modifier and entity would be their own lexemes and tokens in the end. Then the next thing that the parser is going to do is go through and match the tokens to production rules. There's a bunch of ways for doing this, but let's step through one, which is the top-down method. So we're going to take the tokens, and then we're going to start with the highest level of non-terminal that we have, which is a query. We know that queries can be broken down into other things in a myriad of different ways. But let's just say we got lucky, and we chose the one that was going to work for our language first, right off the bat. So we say, OK, query can be broken down into a term and another query. Does that work with the tokens that we have at hand? Yes. Yes, it does. We can't break down a term anymore. We can't break down a query anymore. Let's try that rule again. Cool, that worked for us because we were able to pop that term off of our list of tokens. Feeling lucky. Let's try that rule again. Oh, no. It didn't work. We don't have another term. Let's try the next rule. Oh, looks like we got maybe lucky this time because let's see. What is a filter? It can be turned into a modifier and an entity. Oh, cool. We got lucky. That was best case scenario, I think. We only had to backtrack once. OK, so I'm running out of time. Luckily, I've reached the end of the talk. I hope if you've learned anything, it's that a parser is just something that takes unstructured language and turns it into structured language based on the grammar that that language is the grammar for that language. When I started this talk, I wanted to learn more about parsers, and once I realized that and I was building my own, it became a lot less intimidating. So I hope, if anything, you take that away, and maybe one day you'll have to write your own search query parser, so you'll have this under your belt, and then maybe you want to write your own JavaScript parser. That's cool too. I hope this helped you. So thank you for your time. Feel free to tweet at me, and you can find my slides at that link. Thanks again.